Hi, everybody. Welcome to the Qiskit third annual Global Summer School. We're super happy that you're all here and that you are all able to register and make it. This is a really exciting year for us. I'm so happy to be able to be here and to be speaking with you all today. As you know, the summer school is going to focus on quantum simulation this year. So I'm going to go ahead and share my screen and we will get started. All right. So, welcome everybody. This is the third annual Qiskit Global Summer School, just like I said. My name is Olivia Lanes. So previous years of the summer school, if you have been involved, if you've tuned in, have focused on a more general introduction to quantum computing, and then more recently, last year, we had a summer school on quantum machine learning. This year, like I said, our topic is quantum simulation with a specific look into quantum chemistry applications. And I'm Olivia Lanes. I am the lead content producer of the summer school this year. I am the North American lead for Qiskit Education and Research. So a little bit about me is that I completed my PhD in physics in 2020 from the University of Pittsburgh, and I studied experimental quantum measurement for my PhD. I joined IBM shortly after that, during the pandemic, just a few months after I graduated. And now I am working at IBM Quantum in a role that allows me to explore both of my interests. I am equally interested in working with students and researchers to push the boundaries of their education and research outcomes through Qiskit using IBM Quantum hardware. And a fun fact about me is that I never attempted quantum simulation or really even knew much about it until late last year. So I learned all of this information that is going to be presented to you this week over the course of just a few months. So I'm confident that we'll be able to explore and learn new things together over the course of these next 2 weeks. All right. So an outline for the rest of the week. So this is Monday. Welcome. It's Monday. Today we're going to focus on an introduction. What is quantum simulation? Why did you even pick this topic for the summer school? And why should I care? And then later on, after we take a short break, we're going to come back and focus on Dirac notation and what I call the quantum facts of life. And then we'll sort of wrap up for the day. On Tuesday, Maria is going to be talking to you all about mathematic prerequisites that you sort of need to have a good understanding of in order to be successful in the following lectures and also introduce quantum circuits. On Wednesday, we are going to review Hamiltonians and time evolution. Thursday will be nature, models, and simulation, and look into classical methods of simulation, their limitations, and an introduction to quantum mechanical methods. After that, we're going to have a lecture by Zlatko on Friday, which will feature an introduction into quantum noise and how to deal with it and why that's even important for quantum simulation in this era. And that's the whole week one. And there'll be 2 labs during this week as well. Week 2 will be an introduction. It will start off with an introduction to quantum chemistry, properties, what to measure, and how do we even know if what we're measuring is correct. Tuesday will be quantum simulation methodology, second quantization, and correlation methods. Wednesday will be static simulation with quantum chemistry, Hamiltonian mapping, ansatz selection, and VQE algorithms. Thursday will be the quantum dynamics simulation lecture, decomposition methods, variational time evolution, and then Friday we'll conclude with our graduation and an expert Q&A panel from leaders across the field who study quantum simulation. All right, so we're really excited to get started. I wanted to introduce you briefly to your professors for this week. I've already introduced myself, but I just want to show you some of the incredibly smart, brilliant, dedicated educators that you're going to be meeting later on in the week. We have Maria, who is a PhD student. She's interning with us. We have Jeffrey, Zlatko. These are both full-time researchers at IBM, along with Panos and Yukio as well, Yeva and Alexander. Yeva, Yukio, and Panos are full-time researchers with us across the globe, and Alexander is also a PhD student. So these are all incredibly brilliant educators who have taken time out of their research schedule to be able to introduce this material and work with us during this week. So we're all super grateful that they could be here and that they were able to dedicate so much time. So look forward to hearing from them later on in the week. All right. Let's just get into it, why don't we? So, why quantum simulation? Why did you pick this topic, Olivia, for the summer school this year? That is a fair question. And just so happens that the origins of quantum simulation as a discipline are almost as old as the idea of quantum computing itself. Richard Feynman, you might have heard of him. He was a Nobel laureate and one of the most famous professors of physics of all time. He worked on the Manhattan Project. He was a great author and a frequent bongo player, which you may not have known. He gave a speech at Caltech in 1959 that was titled "There's Plenty of Room at the Bottom." And this was essentially a call to action to join an entirely new field of physics dealing with the microscopic. During this lecture, he actually issued two challenges to the audience, worth $1,000 each, which at the time was, kind of a lot of money. The first was to construct a really, really tiny motor. And this was actually solved the next year by a graduate student, William McLellan. And then the next challenge was to scale down the text of a book so small that it would fit on the head of a pin. And this took a much longer amount of time to solve. It wasn't solved until 1985 by another graduate student, Tom Newman, who reduced a paragraph from A Tale of Two Cities into 1/25,000th of the scale in linear size. So that's pretty incredible. So he issued these two challenges as sort of a way to motivate people to start thinking about the incredibly small. He also spoke at this lecture about how it should be theoretically possible to use a quantum mechanical machine to simulate quantum materials. And he said it should be it should be in principle possible, I think, for a physicist to synthesize any chemical substance that the chemist writes down, to put the atoms down where the chemist says, and so you have to make up your own substance. And it took a really long time, actually, before people took this super seriously and saw the gravity of what he was saying in his lecture. And by the 80s, there was another gentleman, Uri Manin, who published this idea of using a finite dimensional Hilbert space, which is the vector space that we use when we talk about quantum computing and quantum mechanics. Um, to model such ideas such as DNA simulation. And this was published in his book, The Computable and Uncomputable. The next year, the first physics conference of quantum information took place at MIT's Endicott House, which is a beautiful campus if you have ever been to it. We were fortunate enough to be able to visit it last year on the 40th anniversary of this conference. So Feynman is again front and center in this photo here, and he was joined by many other incredibly influential physicists at the time, such as Dyson and Crutchfield, Toffoli and Landauer. And just as a fun fact, Charlie Bennett, who is one of the fathers and the creators of quantum cryptography, is actually the person behind the lens taking the photo in this picture, and he is now an IBM fellow. So, anyways, they got together over the course of a few days to discuss these ideas. And this is just a zoom in of all of the incredibly famous people who were there. Like I said, we have Feynman front and center, Landauer, Toffoli, Rothstein, so many incredibly influential people. And Feynman gave another keynote talk called Simulating Physics with Computers. He proposed the idea now of using quantum computers to simulate quantum systems that would be basically just too hard for conventional classical digital computers. And it was later published in a transcript to be able to be passed on and read across the country. And he said in his keynote that it would be inherently important to use not only what we learn in the physics lab for physics, but in other subjects as well. And simulation will provide this key bridge between theory and experiment. It will help identify deficiencies in the theory and help develop new interpretations. And these computations will lead to scientific breakthroughs. All right. Now, what can you do with a new kind of computer, right? This is what he concluded at the end of his keynote. A quantum computer, as it turns out, as far as I can tell, that you can simulate with this quantum system with quantum elements, not a Turing machine, but a machine of a whole new kind. So now we've reached the point where I want to discuss 4 incredibly important questions from Feynman's keynote lecture. The first is, what even is a simulation? And from here on out, I'm going to define a simulation as a computational model that will do exactly the same as nature will do. So you might be familiar with numerical methods. You might have even heard of the Monte Carlo method for numerical simulation. This is inherently different than what we're talking about, though, because these numerical methods only offer approximate solutions to a system. We're talking about something that will do exactly the same as what nature would do. Feynman also pointed out that the computational elements required for simulation must be proportional to the space-time volume of the physical system you're trying to simulate for it to be useful. And also, you can't have long distances for communication paths when you talk about simulating something as well, because when you have long distances, it of course takes a finite amount of time for the information to travel across those distances, and that's not what would happen in nature in a real simulation, right? So that is what a simulation is. The next important question, can classical computers simulate classical physics? Well, something that's interesting to consider is that both time and space are continuous, right? They can be broken down into discrete elements, though, if they're sufficiently fine. And this is because classical physics is deterministic. And the way that I like to describe this is that if you take a ball in a Newton's cradle, that's one of those devices here at the bottom, one of these balls on a string, and you pull it back a certain distance and you let go, the balls on the other side will swing and hit it, and it'll go back and forth. If you've ever seen one of these things, it's kind of cool. It's a demonstration of it, momentum. If you bring the ball back, 10 out of 10 times, it's going to do the exact same thing because nature in classical physics is deterministic. Something leads to something else. A leads to B. There is a cause and effect. So discretizing nature into sufficiently fine elements can make the passage of time be able to be simulated perfectly fine because no information is lost. All right. So we can put a little check by this, right? Classical physics is able to be simulated on classical computers. There's no problem here. Next, can classical computers simulate quantum physics? This is question 2. Now, quantum mechanics, if you don't already know, and we will explore later on, is a probabilistic theory. If you set up an experiment with a quantum-sized ball at the same speed and the same momentum 10 times, you're not going to get the same result 10 out of 10 times as you would have in the previous slide on the previous experiment. And so you would get instead different outcomes with associated probabilities of each outcome. So if we discretize time up into little chunks now, if we're talking about a quantum mechanical experiment, this no longer solves our problem because there's not a perfect cause and effect relationship during these little chunks of time. Probabilistic configurations cannot be computed on a classical computer. And if we look at the complexity of the problem as well, if we want to configure a problem, for example, say with R particles at endpoints in space, you would need an exponentially large number of resources in order to be able to compute this, which is just too large for a classical computer. So essentially, there are just too many variables that have to be kept track of when you're talking about a quantum physics simulation. So we're going to put a little X here, right? You can't completely simulate quantum physics on a classical computer. So TLDR, too long, didn't read. The answer is no. Now, can quantum physics be simulated on quantum computers? This is the last question, one of the most important ones. So, yes, it's true that the size of the computational space grows at the same rate as the space needed for simulation. And for simulating intrinsically quantum mechanical systems, such as molecules, atoms, quantum computing is extremely promising because qubits can be used to represent the natural states in question. So our conjecture is there is, in fact, a universal quantum simulator which is physically realizable that can simulate any physical system. And I'll leave you on this slide with just a meme from the Legally Blonde movie. If you've never seen it, you should go see it. But basically, quantum computers can do what classical computers can't do because it's intrinsic to their nature to be able to simulate probabilistic quantum mechanical simulations. And at the very end of his lecture, Feynman wrapped up his speech by saying, and this is a really famous quote now, nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. So what he said was basically that we have this incredibly interesting field of physics to look forward to. It's not necessarily going to be easy, but the promising applications are immense. Now, before we go on, just want to talk briefly about the necessity of quantum simulation. And so there are sort of two classes of applications. One, problems that are efficiently solvable on classical computers that allows us to experimentally address intriguing questions, or sorry, on quantum computers that are not directly tractable in the laboratory. Say you want to simulate things that you just can't reproduce. You might be talking about, interactions around a black hole, for example. You're not going to create that in a laboratory. And a system with more than 60 qubits can't be simulated with a classical computer. And furthermore, something on the order of 100 qubits, 100 quantum bits, a moderately sized quantum processor could outperform supercomputers for these exact solutions. So the complexity is very much in our favor when we're talking about quantum versus classical. And that's why the necessity is there. One other important thing to note here that I thought was really interesting is that chemistry simulations account for at least 30% of computational time on supercomputers these days. So over almost a third of the time that supercomputers spent running, what they're doing is trying to simulate chemistry. So this is a huge field with a lot of time and energy and money and resources being dedicated to it. And you can see from just the amount of time that is being run on these supercomputers that's not very efficient and that we don't have a better replacement for it. And that's why we're so interested in quantum chemistry as a possible application for quantum simulation. All right, now I just want to briefly pause and mention where we are and some of the state-of-the-art work that has been done in the past few years in the area of quantum simulation. This is a really cool paper that was published recently on simulating quantum many-body dynamics on a current quantum computer. And this showed that although the quantum computers are still noisy, we're still in the noisy intermediate scale quantum era, you are still able to extract some useful pieces of information and really see the quantum dynamics at play here. Even though there's noise, those real effects are still visible. So that was really cool to see. And then this is another paper that's a few years older, but at the time it showed that we were able to simulate the largest molecule yet, beryllium hydride. It just has 3 atoms, but there is proof here. It's the proof of principle that really counts because it shows us that we are able to simulate atoms and quantum effects on these computers as well, these quantum computers. So the later half of this school is going to focus on quantum chemistry solely as an application for quantum simulation. And that's because it's one of the most interesting focuses and because of its accessibility to the subject through Qiskit. So unsurprisingly, chemistry deals with molecular reactions, which are at the quantum scale, and thus exact simulations for all but the smallest molecules, like I mentioned on the previous slide, are intractable for classical computers. There's also a fair number of quantum algorithms that have already been shown to be useful and precise for chemical reactions and dynamics. So there are plenty of interesting use cases, and many more details are going to be discussed later on in the summer school. But these are just a few images that were taken from recent IBM papers focused on entanglement foraging and quantum chemistry algorithms. And you're welcome to look these up, but some of their ideas and their findings are going to be discussed later on in the summer school as well. So, at a less granular level, quantum simulation in the future hopes to be used for some really exciting applications, such as the discovery of new materials on the molecular level, which could be used in medicine, quantum sensing, among others. There's also this idea of drug design. Since chemical reactions in the brain with drug interactions really aren't well understood, it's possible that simulating these interactions more efficiently could lead to some barriers being broken down and will enable discovery and development of medicine that could really help people. Lastly, there's also this concept of battery development. And if you ask any chemists you know these days, many will tell you that it's not really well understood what goes on in a battery at a molecular level. Furthermore, green and more efficient battery development is a huge area of interest for car manufacturers, the government, and elsewhere as well. So this list is far from comprehensive, but I hope it gives you a good overview and sort of sparks some creativity and imagination about where we're trying to go with some of these experiments in the future. All right, now we are at the part of the lecture where we're actually going to talk about what a quantum computer is and why we're going to be using it going forward for quantum simulation. And the way this lecture is organized and set up is to make sure that we're all in the same playing field. So some of this stuff may seem super basic, but I promise it's not going to remain that way throughout the entirety of the week in the summer school. We're going to start at the very beginning. It's a great place to start to make sure that we're all on the same page. And if you're bored and you're like, yes, yes, Olivia, I've heard what a qubit is a million times, just hang out and sit tight. I think you're still really going to enjoy some of the material here. I know that I personally have been introduced to this material probably 100 times at this point in my life, but if you let yourself just really be immersed in it for a few moments, I think it never really ceases to amaze me at how interesting it is. So just give it some time, all right? Let us dive in. All right, so let's begin with classical computing. I said we are going to talk about quantum computing. We're actually going to talk about classical computing at the beginning for just one more second. And this is because this is how it's easiest to explain what quantum computing is and why it's so different and weird. So with classical computers, they complete computation using bits, right? I like to think of this as a light switch. It can be up or down. Some people prefer bar magnets that have a north and a south alignment for their poles, or a coin, which has heads or tails. But basically, the idea is that it has two elements, and that's it. Bits are used to encode all information that you interact with and put in a computer. So every video game you play, every small computation you do, it's all broken down into these bits. So just as a fun example here, we have this idea of colors. So if you want to encode colors on a computer, on a classical computer, you can do this first with the idea of the coins. You can say, red is equal to 3 coins, heads, heads, heads. And we know that for all these colors here, we're going to need 3 coins because I have 8 colors and 2, because we have 2 ways to express our information, heads and tails, to the 3 is 8. Let's say that orange is heads, heads, tails, and so on. I've laid out a whole chart here for you, which Tom Wong does an excellent job of describing even further in his book, and I'll link that at the end of the PowerPoint if you're interested. But in binary code, we can also say, heads and tails is the same as zeros and ones. In binary code, this is what it would look like over here on the chart all the way on the right. All right. So say we also want to use binary code to convey numbers, which is really important to note for later on. This binary code 11010, for example, is how a computer would store a specific number. But what number is that? It's not 11,010. So the way that we can extract the number that we're familiar with from binary code is to break down every single digit of this binary number and see what factor here exists. So for example, in the 0th place, we have 0 times 2 to the 0. That's 0. In the first digits place, we have 1, because there is a 1 there, times 2 to the 1. It's the 1th place. And for the third digit, it's a 0 again. 0 times 2 to the 2nd place, because it's the 2nd digit. The third digit, but it's the 2nd place. All right, so that's how you do it in binary code. And then you just add up all these numbers together and you will see that the digit that we're trying to represent is 26. So that's how you encode information on a classical computer. That's how bits work. Now let's go back to that idea for a second of that magnetic bar needle from the previous slide. I want you to imagine it shrinking down until it's almost invisible and it looks just like a tiny magnetic needle with an arrow that points from the South Pole to the North Pole. So now instead of just aligning in a field, if it's uniform, we're going to look at an inhomogeneous field, a non-uniform field. And what would actually happen is the needle would start to precess, which is sort of hard to visualize, but it's basically if you move your finger around its point like this is what the magnetic needle would do in an inhomogeneous field. And so you can also sort of visualize this with a top spinning in a gravitational field. It's the same sort of movement. All right. And basically, we need to consider this because this is the best visual picture we have for this magnetic needle that is intrinsic to atoms. We call it spin. And this property of spin is actually a property of quantum objects, not just atoms, but electrons as well. And it's not super important for the context of this lecture to understand what a spin is. The best thing that I can do for you at this point is just say, imagine it's a ball, it's rotating, except it's not a ball, it's not really rotating. So if you ask me any further, that's what I'm going to tell you. But basically, the idea of spin is like a magnetic needle. The other thing that we need to understand is this idea of projections from the magnetic needle, and it's related to the displacement within the inhomogeneous magnetic field. So if you look at the arrow from the side here, the length you would see is the projection of the arrow, okay? So if you pretend like you're just looking at the arrow from the side, you would see not its entire length, right? But you would see what's outlined here between these dashed lines. As some other examples on the right-hand side here, you would see that the largest projection that's possible is when it's completely aligned in the field, right? That's when you would see its entire displacement of the magnetic needle. A small projection would be when there's a small angle above the perpendicular line that you could draw from the field, because then you would only be able to see from the side a small projection. You would see no projection whatsoever. You would see zero if it was completely perpendicular to the field. And then in addition, you can see negative displacements as well if the magnetic needle is pointed down from where you would draw that perpendicular line. So there can be any sort of projection. I just wanted to visually show you some examples here. All right, now we are ready to go ahead and discuss one of the coolest experiments in all of physics, in my opinion, the Stern-Gerlach experiment. And the Stern-Gerlach experiment was conceived by Otto Stern in 1921 and was performed by him and also Gerlach in Germany. And they were two scientists basically looking at the properties of silver atoms in the presence of an inhomogeneous magnetic field, which is why we spent so long in the previous two slides talking about magnetic fields. So just as I described before, they would have these silver atoms, which have these spins, these magnetic needles associated with them, and they wanted to see what would happen if they shot them through this inhomogeneous magnetic field. So in the field, they would expect these magnetic needles intrinsically inside them to be deflected either up or down with a force that is proportional to the projection of the needle. So for instance, if the projection of the needle was positive, it would experience a large force and be projected up greatly. On the opposite, if it had a large negative projection, it would experience a large negative force and be projected down by a large displacement. But these are sort of the extrema, because most of the atoms, if they were gathered randomly, would have a projection that would not be totally positive or totally negative, right? Most would fall somewhere around zero and not be displaced at all. Most would fall somewhere around this point in the middle here, right? This is what they hypothesized would happen from a random assortment of atoms. This is the expected outcome. At the end of shooting millions of magnetic silver atoms through this field, they expected to see something like this, which would represent a normal distribution here in blue of the projections, where, like I said, the average would be just about zero, and it would be grouped about that average with very few on either end. because these would sort of be the extrema and a continuous sprinkling of atoms in between them as well. So that's what they expected to see, but that is not what they saw. This is what they actually saw. So what actually happened to Stern-Gerlach was that they saw two discrete clumps, only two distributions on either side here with some finite width, but there was nothing in the middle. There were no atoms at all that could be seen that were deflected anywhere above a very high positive or very low negative deflection. How could that be? So if we look at the results again, we could see, well, Stern-Gerlach saw that these deflections were actually integers of what we call the Bohr magneton. And they came to describe these two clumpings as atoms that would have a spin up. Let's just label that with this funny little symbol here for now. We're going to give it an up in this weird little bracket notation, or a minus, a negative in this weird bracket notation. We would say it's spin up or spin down. And so the conclusion is the magnetism of these silver atoms only had two states. They basically only could feature a spin that was pointing straight up towards the North Pole or straight down towards the South Pole, but there was nothing in between. So it wasn't exactly as I described before, because that was sort of a naive guess that there would be a lot of atoms with random distributions in the middle. In fact, that's not the case. The atoms have a quantized spin, so up or down, spin up or spin down, that is all. So now let's take a look at a little bit of a different experiment. Let's compress the idea of the original Stern-Gerlach experiment into what we call the Stern-Gerlach apparatus here. And you'll notice I've changed the alignment of the spin of the silver atoms now to sort of reflect reality. Sorry, I tricked you on the previous slide. I wanted to highlight what the experimenters at the time expected to happen. But now we know that they only had a projection up or down. So you can see here that these are fully aligned with the vertical. So the entire experiment is shrunk down into this tiny box, and we call it the Stern-Gerlach apparatus. So atoms go into the box, and if they experience a deflection due to this inhomogeneous magnetic field, which I'm just pictorially describing here with a gray arrow pointing north, then they would experience a deflection up if they're spin up, or down if they're spin down. And there were two exits for them to leave the box, only two. There was one at the top, one at the bottom, one for spin up, one for spin down. And if you take a random assortment of atoms, what you will see is 50% will come out of the first opening at the top, and 50% will come out of the bottom opening, the minus sign. Okay? So now let's look at some probabilities and some interactions with multiple boxes. So the first we're going to look at is the Stern-Gerlach apparatus that we just described on the previous slide. It has an inhomogeneous magnetic field, two openings for the spin up and the spin down atoms. Only we're going to ignore all of the atoms that leave through the negative exit for right now. Let's just gather them all and throw them away. You don't have to picture what happens to them at this point. All of the atoms that leave through the positive side, however, all of these spin up atoms are going to be put into another Stern-Gerlach apparatus. And so what we find with this experiment is that all of the ones that leave through the second apparatus are also spin up. We have 100% of the distribution that leave through the positive exit from the Stern-Gerlach box and 0% that leave through the negative opening of the box. So this is probably not too surprising, but it's just to show you that the box itself does not just scramble the amount of atoms that have spin up and spin down within them. All right. The next experiment that they did was to flip the direction of the inhomogeneous magnetic field for the second box. So they basically just anti-aligned it and rotated it. Let's say this was the z-axis originally. It's now aligned with the minus z-axis, but it still has the openings for minus and positive. Only this time, because we've anti-aligned it, all of the atoms must come out the top. So they're all spin down at this point, or they have a negative spin correlation. None come out the positive side because it is anti-aligned. Okay? All right. All right, now this brings us to the crucial experiment. Let's take a Stern-Gerlach apparatus, the original one, that is aligned towards the z-axis. We're going to ignore all the atoms again that are spin down that come out of the first box. And then we are going to place a second box after it that is now aligned with the x-axis, so it's completely perpendicular to the first box. And then we are going to place a third box after we ignore, again, all of the negative spin down atoms that come out of the second box at the end here. So this is the original box, the same as the first box, aligned with the z-axis. So let's take a moment here and guess. What do you think will be the outcome? What will be the distribution of atoms that come out of the third box? I'll give you guys just a second here to think about it. Okay, time's up. So if you said 50-50, you are correct. Again, this is shocking unless you are already familiar with quantum mechanics. Because think about it, we tried our absolute hardest to ignore all of the negative spin atoms. We got rid of them in the first box, we got rid of them after the second box. We tried super hard to get rid of all of them. And yet at the end, we still ended up with half of them coming out with a spin down measurement. And this highlights a feature of quantum mechanics, which is that some measurements don't commute, meaning they are actually incompatible with one another. And as it turns out, you can't measure atom spin on the z-axis and then the x-axis with any type of correlation. All right? So the measurement of the x-axis projection of the atoms destroyed the information from the z-axis projection. All right. More on this later. You might ask why we're spending so much time on the Stern-Gerlach experiments, because they don't technically have to do with quantum computing, right? But not only is it a fascinating experiment, but it is actually one of the first demonstrations of this quantized nature of an atom, and thus it's almost demonstrating what we like to call a qubit. All right, next I want to talk about, just briefly, another one of the most interesting and important experiments in all of physics, which is the double slit experiment. And this highlights the strange nature of quantum mechanics as well. In the double slit experiment, you shoot electrons through a double slit apparatus, and you will see an interference pattern on the other side. So classically, what you would expect to see is just two highlighted spots, right? So you would see a distribution where the electrons went in through the first slit, or a distribution where they went in through the second slit. So they would go in one or the other, but nothing in the middle. But what we actually observe is this distribution pattern here on the bottom. You might think that this wave pattern could just appear due to the interference of the electrons maybe bouncing off one another as they go through the slits. But actually, you will see this pattern even if you shoot the electrons through one by one. This pattern will still appear. Unless you physically watch which slit, or put a detector after each slit to see which slit the electrons went through. Then you will see the pattern that I described previously, what is referred to here as the particle pattern. But if you don't watch which slit the electrons go through, you will see the bottom pattern, the wave pattern here. And so unless you physically watch which slit the electron goes through, they will interfere with itself and go through both slits at the same time. And this highlights the superposition principle of quantum mechanics, which is fundamental for not just understanding quantum mechanics, but for quantum computing as well. All right. I hope that you weren't already numb to the idea of how cool quantum mechanics can be, because one of my favorite quotes here that I just want to pause and think about for a minute is that quantum mechanics forces us to the brink of implausibility, but not beyond. All right? If you're hearing this for the first time and all this seems normal, you might want to rewind a bit and make sure we're all on the same page here, because this should seem very weird. And the reason that it's so weird, the reason that the electron was able to interfere with itself on the previous slide is due to this principle of quantum superposition. It was not going through one slit or the other slit. We didn't make it choose. It was going through both, demonstrating this behavior of something that's like a wave, and we call this a superposition. When we say that when a particle is in a superposition like that electron, it's some combination of two things or more. So we can say it's some combination of one slit, some combination of the other slit, or it's some combination of spin up, some combination of spin down, right? I'm just using the same notation that we had before, the plus and the minus. but nothing else. And if you want to write this state as a quantum mechanical state, psi, we can write that as plus, minus, plus, depending on the state, that negative state. All right? And that's how you would write a superposition visually. All right, so now we are at our conclusion page before we get into more quantum computing itself. So what is true? What must be true at this point? Single particles can exist in states of superposition, which combines multiple measurement states with certain probabilities associated with them. Single particles can interfere with themselves due to this nature. And upon measurement, only these definite states can be observed, and the outcome is probabilistic, not determinate. All right? So when you actually go about measuring something, you won't be able to see the superposition at all. You will only be able to see the measurable states. Before you measure, they can exist in this superposition. And we can picture this on a qubit, a quantum bit now, as something on the Bloch sphere. That's what this red and blue sphere highlighted here is supposed to represent. So on a Bloch sphere, there is a vector that points from the center of the sphere to the two measurable classical states, which we're going to call from now on 0 and 1 instead of plus and minus, but it doesn't really matter what you call them. There are two discrete states that are able to be measured. And if the vector is pointing to the north pole, we call that the 0 state. If the vector points to the south pole, we're going to call that the 1 state. And if the vector points to any other state on the surface of the sphere, that's going to be representing some combination of both 0 and 1, and that's going to be a superposition state. And we'll explain this notation a little bit further later on. But visually now, I want you to picture a quantum bit as a three-dimensional bit instead of a classical bit, which is two-dimensional. So now how do we build a quantum computer from these bits? This is what's referred to as the DiVincenzo criteria. The scientist DiVincenzo laid out basically a set of rules that you would need to check off one by one in order to say, well, I have a quantum computer now. And the first are qubits, quantum bits. We call these our well-behaved quantum systems. And again, you can visualize this as a sphere, as a Bloch sphere. I've now outlined the states as excited or ground, 0, 1, doesn't matter. And you need to be able to initialize these qubits into well-known states. So if I want my qubit to start off in the E state or the G state, I need to be able to reliably put it in that state time and time again. I also need to be confident that these states will have relatively long coherence times, meaning it will stay in the state I initialize it in and not just decay into the ground state before I can run quantum algorithms and quantum gates on it. Lastly, I need a universal set of quantum gates and a qubit-specific measurement capability, meaning that I can individually measure every single qubit in my system without perturbing the other qubits as well. And we'll talk about what quantum gates are later on, but this is what you need in order to say I have a quantum computer that is ready to do quantum simulation. And now a fair question to ask at this point is, Olivia, is this even possible? Can we even build these systems? And while it might be fair to say it's impossible to know for sure, I always like to point out that in 2012, it was Nobel Prize worthy just to be able to control and measure one individual quantum system. And in fact, these gentlemen, Hiroshi and Wineland, won the Nobel Prize for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. That was just one quantum system. And now, years later, we have invested a lot of time and effort into building systems that have over 100 qubits in them at once. And this is a picture of Dario, who's the director of IBM Research, standing next to the IBM Quantum System 1. And this is a picture of what's inside it. This is a dilution refrigerator. So again, this is only 10 years, which is not that long if you really think about it. So there's a lot of reason to feel very optimistic about the future of this field based on the rapid progress that's being made. All right, I think this is a good point to take a break, actually. So why don't we all take a quick break? I'm going to go get some water and some coffee, and we will resume in just a few minutes with some mathematical basics. Okay? All right. See you all in a few minutes.